Hello and welcome to this FP2 exam paper walkthrough. This was January 2024. We were allowed a calculator and the formula booklet. Question 1. Using algebra, solve the inequality this. Now here, what I would normally do is multiply both sides by the square of the denominator. So we get x plus 2 squared over x plus 2 here. 2x plus 3 times x plus 2 squared here, and of course one of those cancels straight away. Then move everything onto one side. So we get 2x plus 3, x plus 2 squared minus x plus 2, and then we can factorize out an x plus 2. We still have 2x plus 3 and one bracket of x plus 2 here, and then just minus 1 here. Expanding out, leave this for now. That gives us 2x squared plus 7x plus 6 minus 1. And then 2x squared plus 7x plus 5. And then if we can factorize that, that would be great. Can we factorize, put a 5 here and a 1 here? Yes, that will work. All of that in order to get the critical values. Here we've got x is equal to minus 2, minus 5 over 2, and minus 1. These are the critical values for this inequality and also the original. This is much easier to sketch. It's going to look something like this. So when is this less than 0? It's less than 0, less than the smallest value, and in between the other two. That makes x less than minus 5 over 2, that first section. And then x is between minus 2 and minus 1 for the little bit here. And it's a strict inequality, so we don't need to worry about the fact that minus 2 wasn't allowed in the original inequality, because it's still not part of the answer. Moving on to question number 2. Determine the modulus of z. The modulus of z is equal to the real part squared plus the imaginary part squared, and then the square root of that. 36 plus 36 times 3, 108. Add those together, we get the very nice number 144. So that gives us a modulus of 12. And of course it's a modulus, so there's no plus minus there. It must be positive 12. Part AII. Show that the argument of z is minus pi by 3. The argument of z is given by the inverse tan y over x, where x is the real part and y the imaginary part of z. So we've got minus 6 root 3 over 6. So that's just inverse tan of minus root 3. And if you put that on your calculator, you will indeed get minus pi by 3. Part A finished. Using de Moivre's theorem and making your method clear, determine in simplest form z to the power 4. That's part B, because we're going to use part A to help us. We know z is this, but de Moivre's theorem is going to be more helpful to have it in modulus argument form, and we've just figured out what the modulus is, and the argument minus pi by 3 like this. So to do z to the power 4, we're going to put all of this on a power 4. And that's good because de Moivre's theorem says you just put the power onto the modulus and then into the argument as a multiplier. So this becomes minus 4 pi by 3. and here as well. Now, what did it say? In its simplest form, I think we could debate a little bit as to exactly what the simplest form of this is. I would say it's in its simplest form there, because 12 to the power 4 is much easier to read than 20,736. But having said that, cosine of minus 4 pi by 3, my calculator tells me is minus a half. And the sine of that is root 3 over 2. So you could argue minus 10,368 plus 10,368 root 3i is a better format. For an exam, write down all three that I've got there. That shows your process here. And it also gives this format, and then it gives this one if they like the brackets, and then it gives this one if they want it all evaluated without any powers or anything. Regardless of which one they want for the mark scheme, that's that one finished. Part C, determine the values of w such that w squared equals z. What I'm really going to do there is w equals z to the power half, giving your answer in the form a plus ib, where a and b are real numbers. So we're doing a very similar thing here. Z to the power of a half, I'm going to apply de Moivre's theorem again, but instead of power 4, power half. So we've got cos minus pi by 3, I sine minus pi by 3, and all of that power half, and then we do the same thing. So that becomes a root 12 minus pi by 6. And they have been a little more specific in the format this time. So if I put root 12 cos of minus pi by 6 on my calculator, that gives me a 3. And the same with sine gives me a minus root 3i. Now we have to be a little bit careful here because it's a square root. So actually, if w squared equals z, I could have a plus minus of this. So there should be two results here. Like that. And that is the question finished. On to question number 3. And here we've got what looks like partial fractions. I always think partial fractions on these, but it's not. Same as the last one of these videos that I did, this is actually going to be more like rationalizing the denominator because of that little plus in there. So I've got r over square root r plus 1 plus square root r minus 1, and to rationalize that I'm going to do more or less the same thing but with a negative sign. I feel like there's going to be a lot of writing in this question. Okay. Here, the whole point of doing this is that when we multiply out the denominator, we end up with those square roots disappearing. We get r plus 1, and then when they interact, the positive and the negative are going to cancel out, and we're going to get the other one squared, which will give us minus r minus 1. In the numerator, we're going to get r times r plus 1 minus r times root r minus 1. And I can see what's going to happen in the denominator, so actually I'm going to leave that in brackets. Because here, as we expand these out, we're going to have r squared plus r minus r squared plus r. These two are going to cancel, and the other two are going to add together to give 2r, which will cancel with the r in the numerator. Very similar to the last question like this that I did. Just finish it off here. And check it matches. Oh, a is a constant. It doesn't say integer. So I guess here a is 1/2. Yeah, that looks okay. Hence, use the method of differences to determine a simplified expression for this thing, and as always, double check that straight away, make sure it actually matches. It does. So we're going straight into what we've just done in part A, and we're summing from 1 to n. So we've got the half, let me put that out the front, and then root r plus 1 minus root r minus 1. So I can actually put that half out the very front, like that, so long as I don't forget that at the end. And then we've got from 1 to n. So to start with, we've got 1 times 1 plus 1, so that's root 2, minus root of 1 times 1 minus 1, so that's root 0. Then when r is 2, we've got 2 times 3, and 2 times 1. It's already started cancelling, that's nice. Just going to do the next one to make sure. 3 times 4, root 12, 3 times 2, root 6, yep, that cancels, that will cancel with the next one here, which means that I only need 2 in the bottom here. So we've got n plus 1 minus n minus 1, and if I take that back a step, then I'm using n minus 1, which in this first one becomes n minus 1 times n, minus n minus 1 times n minus 2, which is kind of horrible, but following the pattern, that one will cancel with the one in the line before it. This one cancels with this one, which leaves me with a very nice answer. So half times minus root 0, which of course is just 0, times just this one square root. And that's it. That is a simpler answer than usual in a question like this. Part C, determine as a third in simplest form the constant k such that this thing, where we're multiplying by k constant, is equal to the square root of the sum of just r. Now the sum of just r, this is one that you might simply know. The sum of r from 1 to n is equal to n times n plus 1 over 2. So the square root of that is the square root like that. Oh, which I think pretty much gives us our answer. Because to make that look like this, we've already got the square root of most of it. It's just this has a divide by root 2 and this doesn't. So if I've got k times this thing from part B has to equal what I just had there, which I know is also equal to this, because you can split your square root when you're dividing, which is equal to root 2 over 2 if you rationalize the denominator there. And comparing that with the left-hand side tells us that k must equal root 2. Now that wasn't too bad. Okay, question 3 done. On to question 4. Part A, determine in ascending powers of x minus pi by 6 up to and including the third power the series expansion about this. Oh, I don't like that 3 over 2 in the brackets there. That is going to be awkward as we differentiate this. Okay, up to and including the third power. So I need the third derivative. Differentiating tan gives me secant squared, but the 3 over 2 becomes a multiplier. So now we need to differentiate this again. And the derivative of secant squared, I can treat that as a bracket like this, and the power comes down, and then you multiply by the derivative of secant, which is secant tangent, and then they combine to give you secant squared again. So what you do effectively is bring a 2 in the front put a tangent on, but then you also have to multiply by the derivative of the thing inside the brackets, which is the 3 over 2. So the 2's will cancel, giving me a 3. And I still have secant squared 3 over 2x now times tangent of 3 over 2x. And I still had the 3 over 2 from the previous derivative, so actually that's a 9 over 2. I hope that was clear enough for you, because we're going to do pretty much the same thing here. Now we need to apply the product rule, and we've got tan on the right, and we already did that up here, so we've got that, and we've got secant squared on the left, and we did that here. So what happened there, if we differentiate our secant squared, is that a 3 multiplier came out the front, so that's 27 over 2, secant squared 3 over 2x, and a tan came into play, but there's already a tan there, so let me call that tan squared. Then you need to leave the secant alone, that's 9 over 2 secant squared 3 over 2x, and differentiate the tan. But when you differentiate the tan, as we did at the very beginning, you get 3 over 2 secant squared. That becomes 27 over 4. Now that looks really horrible, but I'm quite happy that we've been able to use the derivatives we've done so far in the question to make that last one quite easy. Or perhaps easy is the wrong word there, maybe I mean quick. 27 over 2, secant squared 3 over 2x, tangent squared 3 over 2x, plus 27 over 4 secant to the power 4 3 over 2x. And there's the third derivative that we need, and we're trying to do it about pi by 6. So Taylor's, let's take a little while there. Taylor's about pi by 6 is evaluated at pi by 6. And then all of the others as well. Like so, where a is equal to pi by 6. Now that's fairly horrible, because I need to evaluate all of these things at pi by 6, and my calculator doesn't have a secant button, which is kind of annoying, but tan at least is a nice one, because if I multiply that by 3 over 2 first, that's just a 1. And okay, secant squared isn't too bad either. When I've gone through that, I get a 2. So 3 over 2 times 2, that gives just a 3. And now I know those, that makes the rest of it easier. That's a 9. And that is 27 plus 27 is 54. Some surprisingly nice numbers in the end. So we've got f of x is equal to 1 plus x minus pi by 6 times 3 plus x minus pi by 6 squared over 2 factorial 2 times 9 plus x minus pi by 6 cubed over 3 factorial, which is 6, times 54. Simplifying all of that. And there we go. That is part A. That was a big part A. Hence, show that tan 3 pi by 8 is this in terms of pi's, where a and b should be integers. Okay, tan 3 pi by 8, that has to equal tan of 3x over 2. That is telling us that x is equal to pi by 4. So if x is equal to pi by 4, then 3 pi over 8, putting that x value into the expression above. Pi by 4 minus pi by 6 is pi by 12. And then here, cubed. Simplifying that, we get pi by 4, and this gives us 32 with a pi squared on the top, and this is a 192 with a pi cubed on top. Make sure that matches. 1 plus pi over 4 is looking good. That means A and B are 32 and 192 respectively. Okay, part B finished. That was it. On to question number 5, polar coordinates. It's an interesting looking curve. Here we've got our initial line. Figure 1 shows a sketch of the curve with polar equation this. The point P lies on the curve where theta equals pi by 3. Often you have to figure that out, but it's nice that they've given us that information. The region R shown shaded is bounded by the initial line of the curve, line OP, where O is the pole, so we're going from 0 to pi by 3 for this curve. Use algebraic integration to show that the exact area of R is that. Okay, we're jumping straight in with the big question, no lead in here. Here's the information, find the area. So we're using a half R squared d theta from 0 to pi by 3. This is a 9-mark question, presumably because R is a little bit more complicated when you square it. So let's go ahead. 100 cos squared theta plus 10 cos theta tan theta, but we've got 2 of those. 20 cos theta tan theta plus tan squared theta. Now I don't like the look of that, but tan theta is the same as sine theta over cos theta. So that simplifies. This one we can change into a cos 2 theta using the double angle formula. Cos 2 theta is equal to 2 cos squared theta minus 1. And the tan squared doesn't look very nice either, but we can use an identity for that as well. That is tan squared theta equals secant squared theta minus 1. And that's much better because we can integrate secant squared directly to give us a tan theta. Over here, let's increase this 50-fold. That's 50 plus 50 cos 2 theta replaces the 100 cos squared theta. So that gives us A is equal to a half of the integration from 0 to pi by 3 of 50 plus 50 cos 2 theta plus 20 sine theta plus secant squared theta minus 1. Okay, let's combine those. And we can integrate this. 49 theta. Cos theta is going to integrate to sine theta with the 2 theta there, differentiating and dividing. Sine is going to integrate to give minus cosine. And secant squared, mentioned earlier, gives tan theta. Now I have to be careful here, the 0 does not make all of those 0. The 20 cos theta is not going to be a 0, but it does make most of them 0. That's 49 pi by 3 plus 25 root 3 over 2 minus 20 times a half, that's a 10, plus a root 3 there, minus 0, 0, minus 20, 0. So at a half times 49 pi by 3 plus 27 root 3 over 2 plus 10. And what format? 1 over 12. So we need to take a 6 out of this. That's 98 pi plus 81 root 3 plus 60. And that should be right. A for pi, B for root 3. So A is 98, B is 81, and C is 60. That didn't seem too bad for 9 marks. Moving on to question number 6. Differential equations. This differential equation describes the motion of a particle along the x-axis. Determine the general solution of this differential equation. Using our usual method, complementary function first, we're going to do m squared plus 6m plus 13 equals 0. That is not going to factorize. So we get minus 6 plus or minus the square root of 36 minus 4 times 1 times 13 all over 2. Into the calculator with that, tells me minus 3 plus or minus 2i. That gives us the complementary function of e to the minus 3 x or t. T a times cosine 2t plus b times sine of 2t. Then we need the particular integral. Up here, 8e to the 3t on the right hand side here. So I'm going to use lambda e to the 3t. Sorry, minus 3t. Oh, that makes me a little bit suspicious if it's going to work because we've got a term here as well. But we'll give it a go. Multiply it by x if it doesn't work. So we're going to try lambda e to the minus 3t. And if we differentiate that, I'm going to write x at some point instead of t. Excuse me if I do, I've already written y instead of x. Okay, that gives us minus 3 lambda e to the minus 3t. Second derivative brings it down again, that's 9 lambda e to the minus 3t. And we want one of those, 6 of those, one of these, and 6 of the first derivative gives us minus 18, and then 13 lambda e to the minus 3t, and that all has to equal 8 e to the minus 3t. That looks like it's going to work. That's 4 lambda is equal to 8, our very nice number of 2. Particular integral then is x equals 2e to the minus 3t. General solution, complementary function plus particular integral, is equal to e to the minus 3t, a cosine 2t plus b sine of 2t plus our particular integral 2e to the minus 3t. And that's x again. Okay, there's the general solution. Given that the motion of the particle satisfies x equals a half and the derivative equals a half when t equals 0, determine the particular solution. Okay, we're going to need to differentiate this. Differentiating the term in front gives us this. And then we're effectively leaving the term in front, differentiating the bracket. So the b sine 2t becomes 2b cosine 2t, and the a cos 2t becomes minus 2a sine 2t minus 6e to the minus 3t. That's pretty horrible. And now we know that x is equal to a half, dx by dt is equal to a half, and both happen when t is equal to 0. So x first, we've got a half is equal to e to the 0 is a 1, cosine of 0 is a 1, that becomes a, sine of 0 is a 0, and then again e to the 0 is a 1, so 2 times 1 is 2. That makes a equal to negative 3 over 2. Not the nicest answer, but okay. Next one, the derivative, also a half. That equals minus 3 times e to the 0 is a 1. A cos of 0, so that's another a, which we know, I'll put that in a second. Plus 0 for the sine again. But then we've got this other term, where we're going to have 2b minus 0 for the sine, and then minus 6 on the end. And we know a is minus 3 over 2, so a half minus 3 times minus 3 over 2 is 9 over 2, plus 2b minus 6, that gives me 8 over 2 minus 4, 2, and therefore b is a 1. A much nicer number. So the solution, x is equal to e to the minus 3t. I always like my positives first, so I'm going to write sine 2t minus 3 over 2 cosine 2t. And we still have the plus 2e to the minus 3t on the end. And there we go. That is our particular solution for the given boundary conditions. On the graph of the particular solution found in B, the first turning point for t is greater than 0 occurs at x equals a. Determine to 3 significant figures the value of a. Okay, we are looking for the first turning point, so basically we're doing a dx by dt equals 0, and then we're choosing the smallest possible value for that. We already have dx by dt somewhere. There it is. That's a horrible thing. That's so horrible, I'm just going to copy and paste. Okay, it's this thing, but with the values that we've found. So b is a 1, and a is a minus 3 over 2. And we're asking the question when this equals 0. So the very first thing I'm going to do to make it all much easier is multiply the whole thing by e to the 3t. I'll also expand the brackets out as we go because that cancels all of the exponent parts. 9 over 2 cosine 2t minus 3 sine 2t plus 2 cosine 2t plus 3 sine 2t. That's good. We didn't really want sines and cosines here. Minus 6 equals 0. So that's 13 over 2 cosine 2t is equal to 6. 12 over 13 cosine 2t. That gives me a 2t value of 0.39479. I'm going to keep all the accuracy on my calculator as I go through these next few steps. A t value of 0.19739, but that's not what it wants. Don't stop there. It wants the x value. So again, a bit of copy and paste here. And I'm not even going to rewrite that. The examiner can see the t value, and I'm going to just put all of that on my calculator. And that gives me an answer of 0.55311 dot 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 to 3, was it 3? 3 significant figures, 0.553. And that is the answer for part C. On to the next question, transformations. A transformation t from the z-plane to the w-plane is given by this. The line in the z-plane with equation this is mapped onto a circle. determine the coordinates of the circle and the radius. Okay, what we're going to do here is rearrange to make z the subject here, and then when we've got z, we're going to split it into its real and imaginary parts so that we can identify x and y, then use this relationship to join them into an equation where we'll have u's and v's because of substituting that in as we go. All of that's happening down here. W z minus 3 to I minus z. The I is going to make it slightly more complicated, but it's the same process. So we isolate z, factorize it out, divide through 2wi plus 3 over 1 plus w. Now in order to separate the real and imaginary parts, we must put in w as u plus vi, because w contains both elements, and to split it properly or fully, you need those elements to be separable. That's why we need to put that in at this stage. Now we need the denominator to be real in order to split this fraction into two parts. So I'm going to collect real and imaginary parts in both denominator and numerator. But of course the I squared there becomes a minus 1. So I can consider this 3 minus 2v plus 2ui over u plus 1 plus vi, and then to make that real in the denominator, multiply it by u plus 1 minus vi. Consequence, we've got to do the same on the top. That's going to give us a fairly messy numerator, but the point of that is that we get a very nice denominator. U plus 1 squared minus v squared I squared, so just plus v squared. In the numerator, 3 minus 2v times u plus 1, and then the other real part will be this one times this one because of the I squared. That will become plus 2uv. Then this one times this one, 2u u plus 1i, and this one times this one, minus v lots of 3 minus 2vi. You can see the real and imaginary parts there, so as I expand all those brackets, I'm also going to split the fraction 3u minus 2v, and then the other two terms 3 minus 2uv plus 2uv, that's nice, cancel those, and that is the real part. Then the imaginary part, 2u squared plus 2u minus 3v plus 2v squared, u plus 1 squared plus v squared I. And the point of doing all of that work was because we know that this is x plus yi, so this fraction is x and this fraction is y, and we know from the question the relationship y equals x plus 3, so we can equate using these two fractions and get rid of the I. So that's 2u squared plus 2u minus 3v plus 2v squared. Don't get rid of the denominator yet because of that plus 3. That just complicates things a little bit. Because when we multiply through to get rid of that denominator, it's going to come up in that little extra bit here. Over here. And then expanding this gives us 3u squared plus 6u plus 3, and everything else is still here. I feel like there's a lot of writing on this one. And then simplifying, We're going to get u squared and v squared, 7u minus 2v, but then plus the 3v is a v, and 6. I hope that's right. We're going to get a few fractions here when we complete the square. We've got u plus 7 over 2 squared minus 49 over 4 plus v plus a half squared minus a quarter, and then we've got that 6 on the end. That gives us a constant value of 13 over 2, and then the brackets are unchanged. And they give us our coordinates, so the center is minus 7 over 2 minus a half, and the radius is the square root of 13 over 2. Okay, next part. The region y is greater than x plus 3, y is greater than, is mapped by t onto the region R. On a single arctan diagram, sketch the circle, shade and label the region. Okay, we're just going to follow through everything that's written with the inequality sign. I'll just do it on the side here. It's still a greater than here. I didn't change the side as I so often do, so that's worked in my favor, leaving that 0 on the left there. So what that's saying is that the circle equation is less than 13 over 2. That means I need the region inside the circle. So sketching this, minus 7 over 2, put that there, minus a half, put that there. So our center point is here. So let's say sort of here. Something kind of like this. Oh, the world's worst circle. Kind of. Okay, it's not too bad because we're going to shade the inside of that and label it R. That was the end of the question. Moving on to the last question, number 8. For all the values of x where the identity is defined, prove that cot 2x plus tan x is equal to cosec 2x. Okay, what I'm going to do is first split these. Let's have sine 2x cos 2x here, and sine x cos x here. And this is, let me do it like this, but on the side, remind ourselves that 1 over sine 2x is what we're looking for on the right hand side to get cosec 2x. So I've got sine 2x in the denominator here already. What I need is the same thing over here. To do that, sine 2x, remember, is 2 sine x cos x. There's already a cos x, so I'm going to multiply the second fraction, top and bottom, by 2 sine x. That gives the same thing here. And here, 2 sine squared x over 2 sine x cos x. Now I'm also going to use a double angle formula for cos 2x. That is 2 cos squared x minus 1. And at the same time use this one here to change that second fraction denominator into sine 2x as well. But now here we've got 2 cos squared x minus 1 and 2 sine squared x, and we can see where this is going now, I think. 2 cos squared x plus 2 sine squared x minus 1, sine 2x, and of course cos squared x plus sine squared x equals 1, so 2 of those is equal to 2. And that is equal to 1 over sine 2x, which is what we needed, because that's the same as cosec 2x. The identity has been proved. Part B, show that the substitution y squared equals w sine 2x remembering that we've just proved something to do with sine 2x, where w as a function of x transforms the differential equation 1 into the differential equation 2. Okay, to save going up and down on the screen, I've copied that. There we go. There's the information from the question, and we're going to transform that differential equation into something involving, up I go, w and x. So looking for dw by dx in the second differential equation. So I know I'm going to have to differentiate somewhere in here, and seeing this y dy by dx is useful because if I differentiate y squared, I'm going to get something very close to that. So I'm going to go ahead and differentiate this one here. That gives me 2y dy by dx. And w, if you remember, is a function of x, so I have to differentiate that times by sine 2x and then leave it alone, and differentiate sine 2x, which is 2 cos 2x. Fairly obviously, the y squared here is no problem. We just substitute that in straight away with the expression at the top. So y dy by dx, if I just get rid of that 2 there and bring it over here and get rid of this 2 here, then I can put that straight in for the left-hand side. First term, I get a half dw by dx sine 2x plus w cos 2x, and then we've got the y squared tan x term, so the y squared becomes w sine 2x. We still have the tan x, and then the right hand side is sine x. I'm not quite sure where we're going with this yet, but let's have a quick look. What did we just prove? Cot 2x plus tan x. Okay, so if we divide everything by sine 2x to get dw by dx by itself, we're going to end up with a cot 2x in the second term and a tan x in the third term. Yes, okay, that looks good. Multiply everything by 2 at the same time. dw by dx plus 2w cos 2x over sine 2x, there's our cot 2x in the making, plus 2w tan x is equal to 2 sine x over sine 2x, and I'll split that into 2 sine x cos x, and then those can cancel. And over here, turn this into a bracket, and the cos 2x sine 2x becomes cot 2x plus tan x, and then we get to use the thing we did in part A. So cot 2x plus tan x is equal to cosec 2x. So this becomes 2w cosec 2x. And the right hand side is a secant x, is that right? Yes, there we go, secant x. So that is our second differential equation. And that's part B finished. Part C, by solving this one that we've just created, determine a general solution for the first one in the form y squared equals. And they've very kindly given us an integral here to use. That's great, because when we use our integrating factor, I can see that that's what we're going to have. We're going to have 2 cosec 2x as our p. Start writing this down. Integrating factor e to the integral p dx is going to be e to the integral 2 cosec 2x, and they've just told us that cosec 2x is a half log tan x, so 2 cosec 2x is log tan x, which makes this a very nice tan x as the integrating factor. Multiply the differential equation by this, we get tan x dw by dx plus 2w cosec 2x tan x equals sec x tan x. Whole point of that is that when we integrate, this is w times tan x, and that might immediately look strange, because if we differentiate w, we get dw by dx, that's fine. But when you differentiate tan, normally we jump straight to secant squared. But if you do a little bit of manipulation, you'll discover that that is the same. It can be manipulated to show the same as 2 cosec 2x tan x. We don't need to go through that now. You can go through that yourself if you've got time. But if you're confident you've done everything correct so far, then you can be confident that this is true. Because the whole point of the method is to get to the point where you can do what we just did there on the left. Now the integral of secant tan is secant, and we need a constant at this point as well. But we need it in terms of y squared. What is w? W is y squared over sine 2x. So we still have a bit of manipulation here. So I'm going to change this into sine x over cos x. And over here, 1 over cos x. Don't forget that constant, because that will create an extra term when we do our multiplication, which we're going to do in just a moment. 2 sine x cos x, sine x cos x, the sines cancel. And we're going to multiply by cos squared x to get rid of those on the left. I did just what I said not to do, don't forget that constant. Times everything by 2 cos squared. Gives us y squared equals 2 cos x. One of those cancels on the first term, but they are both here on this second term. And if you want to, you can turn 2c into some other constant, but I'm quite happy with the 2c there. I don't mind that. And I think we are finished. In terms of cos x, and we've left it at y squared. Yes, that looks good to me. Moving on. No, we're not. That's it. The end of the paper. So I hope that was useful for you.